right, 5, 4, 3, 2, 1. We are live. This is Retraice number 67 for Thursday, December 1st, 2022, 11 p.m. Eastern, 8 p.m. Pacific. Retraice is about what's going on out there. The short answer to that question is computer control. Go back, see what we mean by that. The long answer is natural, artificial, and strategic intelligence. There's an even longer answer than that. It's probably the whole podcast up until a few segments ago. And finally, humanity, which is the best part of what's going on out there. But Retraice is for outsiders, and we found that the computer control game is player-oriented. I'm trying to do it from memory. It's hard. It's a lot to remember. I'm going to start doing review episodes. Don't worry. So the computer control game is player-oriented, and so now we're learning to play, which is sort of like teaching ourselves artificial intelligence, engineering, maybe, whatever. Today we're going to talk table-driven agent, our most basic, our most first, our most page 48 thing in AIMA4e, Artificial Intelligence Modern Approach, 4th edition by Russell and Norvig. We've talked about the pseudocode. We've talked about the Python implementation. We've talked about that twice. It took 2 days to kind of get through that. Now we're going to talk about the mathematical destiny of our dear friend, table-driven agent. We're live. We're going to do math live. We're actually not going to do math. We're going to explain math. The math was already done earlier today. Disclaimer, and I'm going to forget to say this as often as I should not be your mathematician. I should be your podcaster. Happy to be that. I should not be your mathematician. If I make mistakes in what you're in the following presentation, it's to be expected. But I tried very hard not to, as I always do. Okay, so with that, let's jump over to what the heck are we talking about here? The mathematical destiny. There it is, right there. That's the number, that expression, that colorful, googly colored expression, not intentionally googly colored expression, it's not an equation, it's an expression. I'll keep reiterating that point. It's easy to forget for newbies. Mathematical newbies. That expression represents algebraically the number of entries we would need in our lookup table to properly equip our table-driven agent. Here's some of the code that makes up the table-driven agent. On the upper left side, you got the pseudocode. On the upper right side, you've got the Python implementation from the AIMA guys, and then down below through the rest of that page, you'll see all the stuff that we did that looks like all this. It's in the Retrace notes if you want to go back. We did that yesterday. Fun and games. But we're talking about the mathematical destiny of that code. What exactly is going to happen if we try and use our table-driven agent to do anything useful at all, let alone to be our final artificial intelligence, our AGI program? This expression tells us what's going to happen. There's going to be a combinatorial explosion. Okay, so I'm going to walk through this sort of almost pedantically because I assume that most people don't spend a lot of time doing anything with summation expressions, using summation notation. So yeah, okay, here we go. And I color-coded it because we're going to try and sort of Englishify it down below. So this is a short way of writing a series of addition expressions. And they would look like, if you wrote them out, something like that. If you had the actual numbers, oops, didn't mean to highlight that. And then something like this, middle one here, if you didn't have the numbers, or if you didn't have the numbers, because even the 1 and the 2, that's our index. Okay, so let's talk. First, when you see the sigma, that's a capital Greek sigma, old-fashioned Attic Greek sigma, you know you're dealing with a sum. You're dealing with a short representation, like this expression here, of something that would be long to write, either the top thing here with algebra covering the things we don't know, or the bottom one is the arithmetic of a situation we actually know that the numbers, know the relevant numbers of which we know the relevant numbers. So you see the sigma symbol, and you know you're dealing with a sum that would look different if we wrote it differently. It means the same thing. Okay, that's the thing to remember. What does this mean the same thing as? It means, okay, so how would we say it in English? Well, first let's say let's try and use summation notation lingo to describe, and just to reiterate, when we evaluate this expression, when we plug in the numbers that we know, when we unfold it or expand it and finally resolve it to a number like 30 or like 16,000 or 4,782,000, blah, blah, blah. When we do that, what do we have? We have a single number that is what? It is the number of entries we would need in our lookup table for our table-driven agent. Okay, the number of entries we would need. We can't forget that because we're going to be looking at this and thinking, oh man, what does that mean? What does it mean again? What does the blue part mean? What is the purple T? Is it the same? It's not an equation, man, but it's on both sides. And the green pinchy thing, ouch. All right, listen, just keep in mind, we're trying to represent a number that is the number of entries in our lookup table. And if you don't remember, let's jump over again. The lookup table, what does it look like in code? It looks like this, okay? It's this thing that starts with the word table and ends with the word thumbs down. Each line represents a percept sequence, a percept history. And so I only made 4 entries in my lookup table because I only wanted to get to the proof of concept, which was, okay, I want our agent to respond with the action thumbs up when it sees red, and I want it to give a thumbs down, a big thumbs down when at the end of the percept history, red, red, green, red. You can actually think of this red, red, green, red as the life of the agent at that point when it gives the thumbs down, when Wayne Campbell gives the thumbs down, okay? So how long does that table have to be if we want to fully specify all the possible percept sequences? If you remember yesterday, I said at one point, by the way, I got some amendments and corrections that I should have done first, but anyway, I forgot. I'll try and do them at the end, otherwise I'll do them another time to yesterday's segment. You'll remember at one point I said that I couldn't give a red, red, red percept sequence because it would corrupt the list in the agent's memory. It wouldn't really corrupt it. What it would do is it would give it a percept sequence that I hadn't specified in the table, and it wouldn't return an action. I don't think it would throw an error, but maybe it would. I didn't run that experiment. And that's most of what you're dealing with. If you specify, we only had 2 possible percepts, red, the word red, not like the color red or some, sensor detecting photons or waves. Red and green. Okay, so those are our only 2 percepts. We kept it real simple. And we only went to a lifetime length of 4 percepts. Okay, and I still didn't specify all the possible percept histories that the agent would have to respond to in a world that I didn't control. If it just lived in a world and it was only going to live for 4 perceptual experiences. Okay, remember red, red, green, red was a 4 percept life that it had. If it was only going to live for 4 perceptual experiences in a world with only 2 things you can experience. There's no ski trips. I've never been on a ski trip. It sounds fun, but it also, anyway, there's no bike rides. There's no falling in love. There's only red and green in this world, in this prison in which we put this poor table-driven agent. I specified 4 possible four percept histories, and I came up way short. This is what happens when you're dealing with a combinatorial explosion. Okay, so this number is going to resolve or evaluate to the number that we need, the number of entries we should have in our dictionary if we want a complete dictionary lookup table for our agent. Okay, so then I tried to write it in using summation notation. You basically the index of summation, the T here is the index of summation, so it appears in 2 places. You could say something like the sum from the index of notation set equal to the lower limit of summation all the way to the upper limit of summation of the term of the sequence raised to the index of summation, but the index of summation does not have to be an exponent like that. It can be a subscript. It can be any place on the involved with the blue part, the P part. Okay. Oh, and I should say, so you know what just algebra symbols stand for? Like lowercase t stands for something, uppercase t stands for something. Lowercase t stands for the percept history, or the number of percepts you're at now. So we start at 1. The percept history is 1. The life of the agent is 1 at the beginning. And when you get to the end of the agent's life, then we represent that with an uppercase T. And in our case, that was 4. So it would have been, if we were to plug in numbers, we would have said, for our agent, we would say the sum from 1 to 4 of this blue P with the lines raised to each term raised to the number of percepts. And you'll see it below. It's kind of hard to say. The P stands for the set of all possible percepts, and the lines next to it just count the number of percepts. So if we just put P here without the bars, we're trying to do arithmetic on a set. It would be like trying to, say, what's red comma green times 2? That doesn't make any sense. You have to put bars next to it, okay, to say the number of things in my set. Red and green are each a thing. There are 2 things in my set. P represents my set, but the bars next to P represent 2. So P is the set of red and green, and bars around P is the number 2. And then we raise that number to the index of summation for each term. Okay, I know it's kind of hard to talk about. All right. The way we would say that in our particular case is the sum from 1 to the total number of lifetime percepts the agent will receive of the number of percepts in the set of all possible percepts multiplied by itself a number of times equal to the total number of percepts in the agent's lifetime so far. I'm pretty sure I've said that exponent correctly, but if I'm wrong, send me a note. I'm 99% sure, but my brain is finite and my time is finite. Okay. So this is what it looks like expanded without summation notation. So first you have, in the middle here, you have the first percept, the number of entries we need if it's only going to have a lifetime of 1 percept. So our agent only sees one thing, red or green. It only needs, it only sees, you need an entry for this first. Can you see my cursor? You can't really see it, can you? You need an entry for this first experience that covers both possible experiences. So our number, our P with bars around it, the absolute, it's not the absolute value, but the value, the number of elements in our possible experiences is 2. So 2 raised to the 1 is 2. Okay, so that thing I've highlighted there evaluates, you'll see below here, to just 2. Okay, this 2 raised to the 2 evaluates to 4. Okay, so this is an algebraic way of saying however many things you've got in your possible percepts, raise it to the power of 2, multiply it by itself twice. Down here, we only have red and green, so our number is 2. We only have 2 things, and then we raise it to the index of summation, which is the number of steps or number of moments in the agent's life, let's say. And then you just keep going until you get to the end of the life, the last perceptual experience of the life of the agent. Then you take the number of possible things, because again, that last moment of life, it can experience red or green, or if you've got blue, red, green, or blue. And man, does that cause the table to explode, okay? But anyway, our lifetime was 4 moments of perception. So this is our first moment of perception. This is our second one. This is our third. And this is our fourth. And for the first moment of perception, we only needed 2. 2 to the power of 1 is 2. For the second moment of perception, we needed more entries. We needed 2 to the power of 2 entries, or 4 entries. And that's like, let's just get off this for a second. What do I mean by that second moment of perception? Like it's this. You can't. I should have put this in the notes. You're not going to get it. It's here are the number of entries we would need in our table for that second moment of perception. Okay, so when you see this 2 raised to the 2, that's number 4. We need 4 entries in our table. Here are the entries: red, red, percept history. Red, 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 green, green, red, and green, green. Those are the number of, those are the entries that we need in our table. If our agent only has a table of, only lives for 4 moments, or lives for 1 moment, we only need 2. If it lives for 4, we need, I'm mixing up my numbers. Lives for 2 moments, we need 4, and then 3 moments, we need 2 to the 3, which is 8, and then 2 to the 4, which is 16. Anyway, trust me, all this stuff adds up to 30. Now I'm having a moment of pause, because if our agent, we might be able to reduce this number a little bit, because we really only need, not exactly sure why we need the first 3 terms. Because if our agent is going to live for 4 terms, don't we only need... Oh, yeah. No, you need... Okay, I thought for a minute there, I was like, oh no, my math is wrong the first time. It's live math, okay? You've never done it before. You never had this much fun in your life. Neither have I. The reason that you need... Let's jump back to the math. The reason that you need this term, even though we know, let's say for sure, this creature is going to live for 4 lifetime experiences, 1, 2, 3, 4 lifetime experiences, is because it has to return an action. You know, the way we've architected it, even after 1 lifetime experience with 3 left to go, it still has to return an action, which means your lookup table has to have 2 entries in it for this moment. This first 1 entry for what action does the agent return when it sees red, and then the other entry is what action does the agent return when it sees green. And then similarly, you have to return 4 actions, or you have to have 4 entries to get to cover all the possible circumstances that the agent has to respond to at moment 2 of its life. And then at moment 3, you've got to add 8. And then at moment 4, you've got to add 16 more entries. And 2 plus 4 is 6, plus 8 is 12, plus 16, plus 8 is 14, plus 16 is 30. I think I said that right. Anyway, that is correct, no matter what faffery I just said. Now, why does this matter? Why is the agent doomed? Well, this is the definition of, if you look at this, if you look at the possibilities for the number, that 30 is on a graph, is on a plot, an exponential curve. This is the definition of an exponential function. Basically, the number of entries you need in your table is f of x equals 2 to the x. And this is only for a red-green world, okay? If we so in a red-green world, 2 to the x is the number, and let's say it's big for all values above 14, which at 14 you get above 16,000. You're adding double the number of entries as the previous time, not the total number, but as the previous step in the life of the agent, every time you add a moment in the agent's life. And then, so this is an exponential function with base 2. Every new term, which is a percept experience, adds one more moment in the agent's life. If we had 3, if we had red, green, and blue, let's say, it would triple the previous term. And so 2 to the 14 is a little bit above 16,000. 3 to the 14 is 4,782,000 and change. 783,000. 4 million. So we go, just by adding 1 more element in the world in which our agent is living, we've exploded, blown the math apart, or blown the table apart, made it impossible. And then they do the math, as I mentioned yesterday, they do the math of 70 megabytes of data per second, and I assume their experience is measured in seconds. So you count the number of seconds, 60 times 60, 3600 per hour. They do it for an hour, and they say you end up with a lookup table for this self-driving taxi of 10 to the 600 billion. 10 to the 600 billion. The number, and they say even for chess, it's like 10 to the 150. And the number of atoms in the observable universe is 10 to the 80. Okay, 10 to the 80 is like a number like this. 10 to the 600 billion is, just writing it is significantly longer. You can't contemplate it. Okay, you can't contemplate the number of atoms in the universe. You certainly can't contemplate the number of entries in the lookup table for this self-driving taxi, or even the number of entries in the lookup table for the game of chess. That's what you're dealing with. Okay, that's it. That's the whole thing. Hopefully that was comprehensible. We got to go one step further. We have to make it so that we can do, I'm, sanity checking my math here and thinking it through carefully. But what we really need to be doing is coding. Always be coding, right? We shouldn't be doing math just, prettifying it in LaTeX here. We need to be using software tools to with facility. Okay, so tomorrow I'm going to get as far as I can with doing this math, and I think it'll be easier to understand when you see it just banging around with syntax highlighting and behavior. Let's make the computer do some work for us, right? So we'll do that tomorrow. Okay, amendments and corrections. This is very important. I've been saying that there's artificial intelligence code and then there's regular classical code or classical, and that the artificial intelligence code, AI code, improves on imprecise answers, and classical code yields precise answers. The steps to yield precise answers are classical, and the steps to improve on imprecise answers are AI code. I shouldn't be saying that. I shouldn't, people are going to get cranky with me about that. I should have put this at the front of the segment. And so I got that from Kissinger et al., the Age of AI. I thought that was the best description of the difference between classical algorithms and machine learning algorithms. But in my mind, I just started to sort of slide the definition over to, instead of machine learning algorithms, I started thinking artificial intelligence code. And a lot of people these days just equate the two. Like, machine learning is what we used to call artificial intelligence. It's been a rebranding since the AI winters or whatever you want to think. But no, machine learning is this and AI is this. Okay, learning is a big section of AIMA4e, but AIMA4e is not all about learning, machine or otherwise. So we shouldn't say that AI code improves on imprecise answers, and you can see that in the lookup table. The lookup table did not provide an imprecise answer that upon which, or our artificial intelligence program did not take an imprecise answer and use the AI lookup table or the dictionary lookup table to improve an imprecise answer. It was just a fully specified classical algorithm that provided by us from the outside. Nobody knows. This is the most important point. I've said this before. Nobody knows what artificial intelligence, or nobody knows what intelligence is, and therefore we don't really know what artificial intelligence is, except insofar as we define it. And nobody gives a really precise definition of artificial. It's in the mind of the beholder, let's say. But for our purposes, we'll be a bit more careful. Let's say the way that I put it was, this is a better way of defining artificial intelligence code. Program steps that include an element, for example, program steps that include an element, we call it the implemented agent function, that make the result of the program dependent upon percepts from the environment and seem to reflect intelligence. Artificial intelligence code should contain what we call an agent function, and it should make the output in response to its input dependent on percepts from the environment, whatever its environment is, if it's just red and green or whatever, and it should seem to reflect intelligence. It's sort of a tautological or self-referencing definition, because we're using the concept of intelligence in our definition of an artificial intelligence. But that's the best we can do. It should interact with the environment, and it should seem to reflect intelligence. Maybe even preferences. Maybe we should say it seems to have some sort of preferences of some sort. But anyway, I'm your podcaster. I am not your AI engineer, nor your AI professor, nor your mathematician, but I am definitely your podcaster. All right, that's it. All references will be in the PDF notes. Retraice.com, Retraice.com. This is segment number 67. Same time tomorrow, 11 p.m., 8 p.m. Pacific. Signing off.